let's do a thought experiment. Let's follow 4,000 imaginary cars on their commute from home to work. Now, their road is a little bit strange. They only have two different paths of 2 roads each. One of these types of roads is a really short, narrow road that depends on the number of cars that's going on the road. That's represented by these T/400 roads. What does that mean? It means, for example, if there's 2,000 cars going on one of them, it would take 5 minutes to cross. Likewise for this road right here. The other 2 roads, the 15 and the 15, they're pretty long but wide roads. No matter how many cars are on them, they'll always take 15 minutes to cross. Now, what's the average time for a car to get from home to work? Well, it's logical to reason that about half the cars will take the top path, half the cars will take the bottom path, and so there will be 2,000 cars on this path, 2,000 cars on this path, making each of these roads taking 5 minutes to traverse, and so it would take an average of 20 minutes to go from home to work. Not too bad, that was pretty easy. Now let's say that we want to construct an extremely high-speed highway that connects the 2 sides of the circle. That seems like it could only help, right? Let's draw that in. So we have a highway that takes only 2 minutes to cross, and it connects all the 4 roads. How does this affect the equations? Well, let's think about it now. What would a car on average do? In fact, let's think more. Would a car ever take one of these 15-minute roads? The thing is, you could always substitute a 15-minute road with taking a T/400 plus a 2-minute road to get to exactly the point where the 15-minute road would take you. But how much is T/400 plus 2? Even if all 4,000 cars were going on one route, that would be 4,000 over 400 plus 2, or 12 minutes. That's less than 15, so it's always beneficial for every car to avoid the 15-minute route. Well, let's think about it now. How much time would it take? It would take 4,000 over 400, 10, plus 2, plus 10 minutes for every single car to get to work. That's 22 minutes. Paradoxically, adding this extra road to our system made the total travel time longer. This is an example of what's called Braess's paradox. Exactly that. Adding roads to a traffic system can actually increase the time that traffic takes. How could this be the case? Well, let's explore with some introductory game theory. To do this, we first got to define a couple of concepts. In the system, we have somewhat of a game. Our cars are the players, and the goal is to get to work. And the different actions they can take are, the roads they drive on. In games, there's a couple of different ways to describe what's going on currently, the system or whatever's happening among the players. The first one is what's called a Nash equilibrium. It's when all players act in their own best interest, in other words, selfishly optimal. For example, in this 22-minute scenario with every single car taking this road and this road and this road, all cars are acting in their own best interest. Every single car individually would lose time if they swapped taking this path, for example, or this path. But that leads us to the next way to describe something that's going on in the game. If it's Pareto efficient, it's when the entire society acts optimally. If nothing can improve the net outcomes of all players. So what would be the Pareto efficient case of this? Well, it would be when no cars would go along this, when half the cars would take the top route and half the cars would take the bottom route. But people are selfish. People will almost always end up taking this faster route because when presented with the opportunity, it's in each person's best interest to get to work faster. And so that's what will end up happening. This is why adding this road to the traffic system can in fact cause an increase in the amount of traffic. Now let's take a look at a physics analogy of the system. We have 2 springs connected by this super tiny white string, and a string connecting the bottom spring to a weight, and a string connecting the top spring to the same weight. It looks like this middle string is kind of holding up the system, no? So what do you think will happen when we cut it? Let's find out. Wow! The actual bottom weight slightly jumped up. How could that be the case? Well, it's actually extremely similar to the scenario we looked at before, with these 2 orange strings being the fixed length 15-minute roads, the springs being the variable length roads, and this was a super fast highway that connected them. It kind of put all the strain on the system, and when we removed it, this strain was able to go equally onto both sides, just like how cars would go on both sides of the circle when the super fast highway wasn't there. So as we can see, these kind of game theory paradoxes happen more often than you think. This is a contrived example, of course, but this is far from the only physics example where such paradoxes arise, and in, of course, many other systems, with traffic being just one out of many to mention. Game theory is actually more relevant than you probably think in everyday life, and I hope we were able to illustrate, a pretty cool example of some paradoxes that can arise, and how you can explain them using pretty simple terminology. Thanks.